All right, so last time we left off here, right, we had a body and we defined surface forces and tractions and body forces, and then we pulled out a little infinitesimal cube from that body and we plopped it on a set of our coordinate system. And just to be clear, this is in the current configuration. Okay, these coordinates are in the current configuration. This body is in the current configuration. So these coordinates are in the current configuration. And we defined this cube. Each of the faces of the cube have a normal vector and a traction acting on that normal vector, and we defined each of those. So the traction in the x1, or traction in the x1 is actually the traction defined by the normal vector on the face and the normal vector n1. Right? Okay. So, and the blue lines represent, so the black ones are sort of tractions in the positive directions, but the blue ones, the things in equilibrium, so the blue ones are tractions equal and opposite on the negative faces. Okay. So now what we're going to do, we're going to cut this cube along a plane like this. So along a plane that passes through these 3 points, we're going to slice that cube. Okay? And so I'm going to draw this slice on the next page here. And so this slice, this plane, we're going to define with a normal vector n hat. So it's a normal vector. And then this is going to have a traction, this face, this slice is going to have a traction vector acting on it that we'll just call Tn. Okay? And this is a vector. Okay. So just to be clear, the components of n, so n is a vector, the components of n are like the cosine of n x1. So it's like the dot product, the cosine of the angle between n and the x1 axis, the cosine of the angle between n and the x2 axis, and the cosine of the angle between n and the x3 axis, right? So these are the components, n1, n2, n3. Okay? This face, this slice, if you will, we're going to say it has surface area delta S. Okay? And just like, as a little aside, if we have an angle, or if we have a line segment L and we have some angle theta, right? The projection of that line segment down onto this axis is like, L cosine theta, right? So that's this distance. Okay. Well, that same concept extends to areas. So if I were to then add a third dimension here and project this out as a surface, then and if this had surface area A, then the projection of that surface area down onto this plane, right, down onto that plane, the projection on the plane is then A cosine theta. Okay? So we're going to use that. All right. Now we have this little tetrahedron over here that, remember, is just the slice of the cube. And that cube was in equilibrium because we pulled it out of the body, right? So it had tractions acting on all the faces, right? So we want to write down an equation, and, you know, having a background in mechanics, when all else fails, what equation do you fall back to? F equals ma. Right? If you don't know anything else to write down, try writing down F equals ma. Okay? So that's what we're going to do. We're going to write down F equals ma. Right? So first, the sum of the forces, right? The sum of the forces. Right? So remember, traction, this vector t is a traction as a unit force per unit area, right? So the force then on this face would be the traction t in times delta s. Okay? Now remember from the previous slide that these blue lines here, right? So these blue lines, remember, this is like t of x2, right? It's like the minus of t of x2, right? And it's acting on well the entire back face, but when I pull out my little tetrahedron, it's acting on that blue face there. Right? Yeah, so over here there's this t of x2, right? So the force on that face then is minus t x2 times n2 delta s. And the n2 comes from this cosine thing, right? So I said that the n2 is the cosine of n with respect to the x2. And so we're just using that same, and then the same kind of area identity, that the cosine of the angle between them, right? Well, here the cosine of the angle between them is defined as n2, right? So we have t x2 n2 delta s. And then we're just going to write down the other one. So we have another vector, you know, something back here, t x1, and another one down here, t x3, right? And so then we have minus t x3 n3 delta s minus t x1 n1 delta s, right? So that's the sum of the forces, and all that is equal to ma, right? So that's equal to ma, okay? Well, I guess I didn't say this, but we can, let's assume this tetrahedron, you know, it's like an upside down pyramid, right? So from this face to the origin is a distance h. Right? So if we do that, then we can write the mass. The total mass is the density times the volume. Right? So then we can say that the density times the volume of a pyramid is 1/3 h, 1/3 the height times the base, the area of the base, and the area of the base is delta S. Right? Okay, so you can see immediately that every term has a delta S in it, so we can cancel those. Okay, and if you remember when we pulled out the cube from the body, right, on the previous slide, when we pulled it out, we said it was an infinitesimal cube, right, infinitesimally small. So if it's infinitesimally small, then what we really want is the limit of this equation as h goes to 0. Right? And the limit of this as h goes to 0, then this term right here goes away. Okay. And then so what we're left with is essentially this guy. All right. And so we have T n is equal to T x1 n1 plus T x2 n2 plus T x3 n3. And remember, we wrote here, just to be painfully explicit last time, that all of these t's, t x1, it's a vector. It has its own components, right? So it's t1 in the x1, t2 in the x1, t3 in the x1, right? So all of those t's are vectors themselves. Okay? So what I want to do for just for a minute, I'm going to take the transpose of both sides of the equation, right? Because remember, by default, our vectors are column vectors, right? So let's take the transpose of both sides of the equation. Now remember, our n1, n2, n3, they're just components, right? They're scalars. They're components of the unit vector n. Okay? But with that, then I can write this equation, right? So then like T n transpose equals, in vector form, n1, n2, n3 times T x1 transpose T x2 transpose T x3 transpose. Right? Now, these are row vectors, right? So T x1 transpose is a row vector. Because by default it's a column, we transpose it, it's a row. So then what I have here is actually a tensor, right? Because each row, each of those 3 rows have 3 entries, 3 columns. So then I have a tensor. Okay. And so this equation, so if I call this, give it a name, this guy is the stress tensor, or specifically the Coachee stress tensor. Okay. And so what that is, what the stress tensor is, it's the tractions in the coordinate directions. And we can write this a little bit, if we give this the symbol sigma, where sigma is a tensor now, okay? We give this thing the symbol sigma, right? Then we can write this equation as T transpose equals N transpose sigma. And it's N transpose because, remember, by default, N is a column vector, and if you look at the way we wrote it here, it's a row vector, okay? So this thing right here has a name. We'll rewrite it on the next page here. So T transpose NT sigma, okay? Now that's a little bit odd looking equation, right? I mean, at least with the transposes in there on the left side, it's a little bit odd. So maybe it's not, but nevertheless, if we take the transpose now of both sides of the equation, then we have that T is equal to what? Sigma transpose N. And this is the way you more commonly see it. And this thing is called the Coachee stress equation. All right, and in indicial notation, we might write Ti is equal to sigma Ji